In this course, we discuss the technologies which convert the energy in solar light into electricity, heat, or solar fuels. Before I come to that, I would like to start discussing the energy source itself. What is light? What are the physical properties of light? And how does a typical solar spectrum look like? Let's start with the first question. What is light? Light can be described as electromagnetic waves, as well as particles with a quantized amount of energy which we call a photon. Let's start with the fact that light can be described by a kind of particles called photons. We have to go back to the already introduced photoelectric effect. The photoelectric effect is demonstrated in the simple movie I found on YouTube. You see here an electroscope. This is an instrument to demonstrate the presence of electric charge. Using static electricity, a bar is charged and the pointer indicates the amount of charge. At the moment, the metal bar is negatively charged by a large amount of electrons. The only way to discharge the electroscope very fast is by putting it in contact with other materials. For the moment, we are waiting until the mechanical fluctuations of the electroscope are damped. Now, the bar is illuminated with a lamp. What we see is that the light is able to remove the charges very fast. If you repeat this experiment with reddish light, this effect does not occur. It only occurs for bluish and ultraviolet light. It was Einstein who explained this experiment in his famous paper from 1905. He proposed that light consists of quantized energy packages, which we nowadays call photons. To eject an electron out of the material, it requires a certain threshold energy. The photoelectric effect shows that when the energy of the photons are above this threshold, the charge can be ejected from the material. If the energy is below this threshold, no electrons are ejected. This demonstrates that light can be described by photons. Now we describe light as a wave. Light can be represented by an electromagnetic wave. Here we see an electromagnetic wave traveling in direction x. Perpendicular to this direction, we see that an electric field E is oscillating. Perpendicular to the direction of propagation and the oscillating electric field, a magnetic field B is oscillating. The distance between the maxima of the oscillating electric field is called the wavelength, usually indicated by the symbol lambda. An electromagnetic wave is propagating with the speed of light c in vacuum. The frequency and wavelength of waves are related with a simple equation. The velocity of the wave is equal to the product of the frequency and the wavelength. The energy of the photon with wavelength lambda is equal to the product of the Planck constant h and the frequency. As the frequency equals to velocity of light divided by the wavelength, the photon energy can also be expressed in terms of wavelength. It is equal to the product of the Planck constant, the velocity of light, divided by the wavelength. Electromagnetic waves exist in many spectral ranges. The visible light spectrum, which comprises of the electromagnetic waves we can see with our human eyes, are only a tiny part of the entire spectrum. The visible spectrum ranges from wavelengths of 400 nanometer up to 700 nanometer, which corresponds to frequencies in the order of 10 to the 15 Hz. At the high energetic side of the visible spectrum, we find the ultraviolet light, which are electromagnetic waves with wavelengths in the order of 100 nanometers. Going to higher energies, we arrive at the X-rays, which have wavelengths of around 1 nanometer, and gamma rays, which have wavelengths of 0.1 nanometer. On the low energetic side of the visible spectrum we find the near-infrared and the infrared light, which has wavelengths of around 1 micron and 10 microns respectively. Microwaves are electromagnetic waves with wavelengths in the order of centimeters. Radio, TV waves are in the order of meters and tenths of meters, and AM waves in the order of 100 meters. The question now is, in which spectral range does the sun irradiate light? For that I will introduce the quantities irradiance and spectral power density. Let's start with the irradiance. The irradiance is the power per unit area and is usually expressed in watts per square meter. The irradiance does not provide us any information about the spectral shape of the light source. In our course we give the irradiance the symbol I. Next, we introduced the spectral power density P, a quantity which has spectral information in contrast to the irradiance. The spectral power density is the incident power per unit area and per unit wavelength. The irradiance and spectral power density are related to each other with this simple formula. How does the spectrum of the sun look like? Or in other words, how does the spectral power density function look like? To human eyes, the sun is a bright object in the sky. The sun, a so-called black body radiator. What is a black body radiator? All matter emits electromagnetic radiation when its temperature is above absolute zero. A body which is not reflective and absorbs all light is called a black body. The spectral power density of a black body radiator, which is in thermal equilibrium, is given by Planck's law. This law shows that the spectrum peaks at a certain wavelength when the object is at a certain temperature. The curve shows the typical spectral shape of a black body radiator. If a black body radiator has a temperature larger than 500 degrees Celsius, it starts to emit electromagnetic waves in the visible spectrum. The higher the temperature of the black body radiator, the greater the shift of the spectral peak to lower wavelengths or higher photon energies. Although the sun is not a perfect black body, nor is in thermal equilibrium, Planck's law is a good first estimate of the spectrum of its emitted electromagnetic radiation. The sun's surface is at a temperature of around 5800 Kelvin and therefore has its spectral peak in the visible spectrum. If we compare this to planet Earth and consider it as a black body radiator as well, its spectral peak would lie in the infrared region close to 10 microns. To test solar modules, we use so-called solar simulators. For that, we use lamps which simulate the shape of the solar spectrum. This is far from straightforward, as regular lamps have different shaped spectra compared to that of the sun. Let's go to the Delft Solar Lab and look at two spectra, one of a compact fluorescent lamp and the other of a color-changing LED strips. The lamps are placed in a black box and spectra shapes are measured using a spectrometer. We see the spectrum of the compact fluorescent lamp. As you can see, its emission has some sharp lines related to the excited states of the mix of phosphorus present in the bulb. Next, we look to a strip of different colored LEDs. The strip of LEDs emits at three distinct colors: blue, green and red. You see the dominant emitted color back in the measured spectrum on the screen. Interesting to notice that it only requires three colors to let the human eye believe we are looking at white light. However, as you can see, the spectra are quite different from that of the sun. It means it requires a combination of many types of lamps to simulate the solar spectrum. If we look at the solar spectrum, 9% of its energy is in the UV range, at wavelengths smaller than 400 nanometers. 44% of its energy is in the visible range, whereas 47% of its energy is in the infrared. So we have discussed that light can be described as an electromagnetic wave and as a flux of photons. The shape of the spectrum of the sun has been introduced. However, the question is whether this is the solar spectrum arriving at the surface of the Earth, and whether it has the same shape and irradiance level. We will discuss that in the next block.